energy systems. This has a lot of cool, interesting information in it. So we're going to walk through this timeline in some more detail, but the overview is that we begin with using our stored ATP as our first burst of energy, then we move to our phosphagen system, then into our anaerobic system, and then finally our aerobic system. So if we look at our phosphagen system, our ATP is consumed, right? That's that stored ATP. But we also have phosphocreatine, or PCR, which is stored in our cells and it regenerates ATP at a really fast rate. And so that's really great because we can use it really quickly. And so as ATP, that stored ATP, that original amount of ATP, and then phosphatin creatine, that PCR, get depleted as we're using them, our body cells are using them to produce energy, then lactic acid, which is a byproduct of the ATP breakdown, it starts to build up or accumulate in cells, and then it signals, hey, anaerobic system, aerobic system, we're going to need your help. And so those systems start kicking in. They don't kick in as quickly, which is why that phosphagen system happens first. Then the anaerobic system, sometimes you'll see it referred to as the lactate system. It takes carbohydrates that are stored either in liver or in muscles. It's stored in its storage form, which is glycogen, is the storage form of glucose. Well, you see blood glucose is the other option. These get converted into ATP. ATP is our body's energy. And this is done via a process called glycolysis if we're taking glucose and converting it to ATP. The glycogen gets broken down slightly differently, but it becomes similar to glucose, a form that we can use it in, and then it undergoes glycolysis. And at the end of glycolysis, we end up making 2 ATP. Okay, so that glucose comes in, it gets broken down, and ends up resulting in 2 ATPs. And so this anaerobic system lasts from about 60 seconds of exercising to about 90 seconds of exercising. Now, as lactic acid builds up, means more and more of it is within our muscles, it actually makes it difficult for ATP to continue to be produced via the anaerobic system, and it causes our muscles to generate less force, and it impairs our coordination. And so when you think about when you sprint really, really fast, then it causes that burning sensation, or your legs feel like you're on fire. That is because of that lactic acid buildup. That's why it hurts to keep running, and that's why sometimes it's even difficult to continue to keep stepping, is because your coordination even gets impaired because of that lactic acid buildup. Now, the cool thing is the majority of this is removed via the bloodstream very quickly. And our body is so efficient and so wonderful that it actually converts some of that lactic acid into fuel in our anaerobic system, the very next system. Okay, but before we get to the anaerobic system, I want to talk about this concept called lactic threshold or anaerobic threshold. And this is the point at which blood lactate begins an abrupt increase, so increase very dramatically. Now, lactate, remember, that's that byproduct of ATP use that we see our anaerobic system and our phosphagen system using. So in really high trained athletes, this lactate threshold where boom, there becomes a ton of lactate in their bloodstream happens between 70 to 80% of their aerobic capacity, or their maximum, as opposed to untrained athletes where it happens at 50 to 60% of their maximum aerobic capacity. And so this idea of lactate threshold or anaerobic threshold is an important one to know about, especially as a coach, because this is a great way to measure fitness and to determine how athletes training. So if we look at this graph here, it's a really great one. You see that the blue line here, this is an athlete before they started training, and then this red line here is looking at an athlete once they've been training for several months. So you see this graph is already marked where the person's lactate threshold is, but remember, lactate threshold is when there's an abrupt increase. When either of these athletes, well, the same athlete, is running at 4 kilometers per hour or 5.5 kilometers per hour, there's some lactate because there is byproduct, but there's not an abrupt increase. And it's not until here at 10 kilometers per hour that this athlete sees that increase really fast. And so this is that lactate threshold. But as this athlete's been training, you notice that their lactate threshold isn't until a higher speed, which means that they're able to perform for a longer time before they see that lactic threshold increase. All right, so once that has happened, let's look at the aerobic system, that last system. So sometimes people refer to the aerobic system as slow glycolysis. It uses carbohydrates and fats along with oxygen to produce glucose, which is then converted to ATP, because remember, ATP is the energy for our body, okay? So if our body is burning fat, fat produces 9 calories per 1 single gram of fat. If our body is using carbohydrates, we can produce 4 calories per 1 gram of carbohydrates. Now, this is why ketogenesis got so popular, because we can use protein if our glucose stores get really low. And so typically we see this happening when an athlete doesn't have enough recovery. So if training's too hard, if the body's not getting adequate rest, or if their diet doesn't contain enough carbohydrates or fats, then we do see protein being used some. So the aerobic system, for each glucose molecule it uses, this system produces 38. I don't have enough fingers to show you 38, but it produces 38 molecules of ATP for each glucose. So when you think about comparing the aerobic to the anaerobic, you want to think about how many ATP are being produced per glucose. So think about which one is the most efficient. Okay, so let's put this all together now. So these are the four, right? These are the three systems, but these are the four different things, the process that our body goes through. This is our timeline, and this is what we are using to produce ATP. So we start with our stored ATP and the phosphagen system, and those can last anywhere from 5 seconds to 60 seconds. That uses ATP. Stored ATP is already ATP. And the phosphagen system, remember, it uses that creatine phosphate. Now, once we get past that 60 seconds or that 1 minute mark, up to 120 seconds or 2 minutes, we move into that anaerobic system, which includes that glycolysis and lactic acid. We mainly rely on carbohydrates for that section. And then finally, after 2 minutes until theoretically forever, hours and hours and hours this system can go. That is the aerobic system, which we mainly rely on carbohydrates and fat. Now, when we look at our muscles and what muscles are using what type of energy, all right, this all kind of comes together. Now, humans have 3 different types of muscle fibers. Now, so I'm not talking about muscles. I'm not talking about biceps or hamstrings. I'm talking about muscle fibers, and this is what makes up a bicep. These are the fibers that make up the inside of a muscle, and we're going to look at muscles in the next section. But there are 2 main categories. There's the slow twitch muscle fibers, and then there are 2 types of fast twitch muscle fibers, okay? And so a muscle like the biceps, it will have multiple fiber types in it typically. And how many of each fiber type is in a muscle is determined by our genetics. So thanks mom and dad for giving us that distribution of fiber type. Okay, so let's discuss these 3 different fiber types. So the slow twitch, oxidative, sometimes called SO or type 1 muscle fibers. Then we have the fast twitch, glycolytic, sometimes called FG, or type 2B muscle fibers. And then we have the Goldilocks of them, the fast twitch oxidative glycolytic. Notice it has oxidative in it, similar to slow twitch. It has glycolytic in its name, similar to fast twitch. This is the type 2A, or the FOG, fast twitch oxidative glycolytic muscles. And so when we look at these, we're going to compare some different information about each of these. So if we look at slow twitch, it takes about 110 milliseconds for these to reach their maximum tension or force. But notice the fast twitch, they're fast, hence their name, and it takes them less than half the time, or 50 milliseconds, in order to reach their highest tension or force they can produce. Now, when it comes to aerobic capacity, slow twitch are slower, and they have that high aerobic capacity. So for a long time, they're able to be used, right? Using that aerobic system. As opposed to the fast twitch type 2, they can only use that aerobic system for a very short amount of time. But this is the Goldilocks one, it can use it for a moderate amount of time. When it comes to aerobic capacity, that really quick production of energy, the fast twitch, it has a very high amount of anaerobic capacity. The fast twitch oxidative glycolytic, it also has a high amount, it's the Goldilocks, and then the slow twitch has a low amount of anaerobic capacity. Now, when it comes to fatigue resistance, this means how long until it gets tired. So the slow twitch, it does not get very tired very quickly because it has high fatigue resistance. And then the fast twitch glycolytic, it fatigues fairly quickly because it produces a lot of force really fast. Now, when we look at glycogen content, glycogen, remember, is that stored form of glucose, and we use that mainly during the anaerobic system, okay? So when we think about that and put it together with the information that we've seen so far, we should be able to guess that the slow twitch oxidative fibers, they have a very low storage of glycogen content, as opposed to the fast twitch glycolytic, they have a very high storage of glycogen content because they use that anaerobic system to very quickly, right, in those first minute, create a lot of force. Now, when we look at the sport types, slow twitch oxidative is more used in endurance type sports because it takes them longer before they can produce a lot of force, and they do not fatigue very easily, right? As opposed to those fast twitch glycolytic is used in more power, things like power lifting, things like gymnasts doing flips tends to be that fast twitch glycolytic with very high power. Interval sports is that Goldilocks because it has some of the slow twitch characteristics and some of the fast twitch characteristics. So it tends to be high amounts or high percentages of slow twitch oxidative fibers in an endurance athlete, as opposed to lots of fast twitch glycolytic in a power style athlete. Okay, so then when you develop a program for your athletes, you're going to want to first assess their current state of fitness. So you're going to assess both their health-related fitness and their skill-related fitness. Then when you go to design that program, you're going to use this 4-phase training plan. And so it is designed as a pyramid for a purpose. The bottom of every pyramid is bigger, the top is smaller. So the bottom part you're going to spend more time on, focus on for longer, and then as it gets closer to a competition, you get further up the pyramid and you hit your peak or the top of the pyramid right before your biggest competitions. All right, so if we look at this bottom phase, that is the aerobic foundation, your athletes should be training at 70 to 84% of their heart rate max for the lactate threshold training. They should be between 85 to 89%. Between the anaerobic training phase, they should be at 90 to 95%, and then the speed training, they want to be at 95 to 100%. So make sure you check out the next video for how to actually calculate these percentages.